In this part, we will try to find out the solution of a linear programming model by the graphical approach. Graphical approach only works for the simple case, such as having only 2 decision variables and a very few number of constraints. However, through graphical procedure, we will realize some important features of the solution to the linear programming, which will help you to build up some intuition to linear programming. Now, let's work on a product mix problem, which is about how to produce 2 types of new computers, max and multi-max, on one same production line. The unit profit margins are $400 for each max and $800 for each multi-max. Both computers need testing and assembly, which are limited resources. We know that testing capacity is 5,000 hours. Each max requires 3 hours and each multi-max 5 hours. For assembly, the capacity is 3,000 hours. Each max 1 hour and each multi-max 4 hours. The question is, how can we arrange the production of these 2 computers to maximize the profit? Now, let's first test our intuition. Since multi-max is much more profitable, should we produce only multi-max? No, your experience in Lego game should tell you this might not be right. We need to analyze it more carefully. Here are the 5 steps we need to go through for using graphical approach to solve a linear programming problem. I will get into details step by step. Step 1. Formulate the problem. It can be further broke down into some detailed procedures. Basically, it is about to specify the 3 components of a linear programming model: the decision variables, the objective function, the constraints. There are 2 types of constraints: resource-driven constraints and boundary constraints. In our computer production example, clearly we need only 2 decision variables, x1 for the number of max produced each month and x2 for the number of multi-max produced each month. For the reference convenience, let's use capital Z to denote the monthly profit from producing max and multi-max. It is easy to see that Z can be calculated from the number of max x1 and the number of multi-max x2 with their corresponding profit margin. As we can see, the total money made from max is 400 x1 and from multi-max is 800 x2. Next, let's configure the constraints. The table here shows the unit resource requirement for both max and multi-max, as well as the resource availabilities. So, for testing, max will use 3 x1 hours in total and multi-max 5 x2 hours. The total usage cannot be larger than 5,000 hours in each month. Similarly, for assembly, max uses x1 hours in total and multi-max 4 x2 hours. The total usage cannot be larger than 3,000 hours in each month. These 2 are resource-driven constraints. We also need boundary constraints, which is by default. for both max and multi-max, we can only produce or not produce. So x1 and x2 are non-negative. Notice in the model itself, we don't require x1 and x2 to be integer, though it makes more sense in reality. So we will first try to find the best solution and to see whether it is already integer. If it's not, we will go to round it to the closest integer. Now we can go to step 2. We need to plot the constraints. Here we focus on the resource-driven constraints. The main idea is for each constraint, we need to figure out the intercept on each axis and then draw the line through them. Hence, we should let x1 equal to 0 to solve x2 by assuming the resource is completely used up. This determines the intercept on x2 axis. Then we let x2 equal to 0 and figure out x1 by assuming the same resource is used up again. This gives the intercept on x1 axis. Finally, connect the two intercepts together. In our example, let's draw test constraint line first, and follow with the assembly constraint line. To draw those constraint lines, we actually assume all the available resources are fully utilized. For testing, x1 equals 0 means no production of max. Then to fully utilize the 5,000 testing hours, how many multi-max has to be produced? Since each multi-max requires 5 testing hours, it is easy to see that producing 1,000 multi-max, all the 5,000 testing hours are used up. Now, we can mark the intercept of testing resource on x2 axis. Next, suppose no production of multi-max, so that x2 equal to 0. To fully utilize the 5,000 testing hours, how many max has to be produced? Since each max uses 3 hours of testing, we know at most we can produce 1,666.7 max in 5,000 testing hours. And this gives the testing intercept on x1 axis. Now connect the two intercepts, and we have the testing constraint line. For assembly, the total available hours are 3,000 hours. If not produce max at all, so that x1 equal to 0, how many can we produce multi-max? Notice each multi-max needs 4 assembly hours. Hence, divide 3,000 by 4, giving us the most number of multi-max we can get, only based on the assembly availability. So that is 750 units. The green dots on the graph shows the assembly intercept on x2 axis. Again, let's make x2 equal to 0. So, not producing multi-max at all. Now, since each max requires 1 hour of assembly, so 3,000 hours of assembly hours can produce at most 3,000 units of max. We have the second intercept for assembly on x1 axis. connect them together. Okay, that is the assembly constraint line. That is the end of step 2. Step 3, determine the area of visibility. The challenge here is to see which side of constraint line is visible. We can figure it out by testing the original point. Plug in the original point, x1 equal to 0 and x2 equal to 0, to each constraint. Include both resource-driven and boundary ones. We can see whether original point is feasible or not for each constraint. Then we know which side of constraint line we should pick. Feasible region means all the constraints must be satisfied. By characterizing feasible region, we actually identify its extreme points or corner points. In our example, we have drawn the 2 constraint lines. And we know the total used testing hours cannot be more than 5,000 hours. To check the original point, we produce 0 max and 0 max. So the total used testing hours must be 0, less than its availability of 5,000. So original point is feasible to testing constraint. And we need to pick the area below the blue testing line. For assembly, the cut is 3,000 hours. Original point means no production in either type and no assembly hours used at all, which satisfy the assembly constraint. So the feasible region suggests we have to pick the down area again. At last is the non-negative boundary constraint. So the feasible region must be so clearly we know the feasible region must be the shaded parts shown in the graph. And in this graph, you will see there are 4 corner points. A is on x2 axis only, C is on x1 axis only, D is the original point, B is in the first quadrant. So step 3 done after we identify all the corner points.